Okay, here we are with a heat engine problem. I like this problem because it reminds us that really all we need to establish a heat engine is some temperature differential. So what's being used here for that is the ocean. So we're saying that there is like a thermocline in the ocean. Those can exist in the ocean where you have two regions of different temperature. So here we have that. There's a region at 20 degrees and at 5 degrees. So the idea here would be someone saying, hey, let's leverage that temperature difference and use it as a heat engine and be able to create electrical power from that. So we're going to have a look at that. So first of all, the first question asks us here for its efficiency, and then the all-important, assuming it is 0.7 times the Carnot efficiency, or 70% of the Carnot efficiency. So cool, that gives us a good place to start here because we are given the temperatures. As we know, though, the temperatures need to be in kelvins for us to utilize them in this way when doing Carnot calculations. So the cold temperature here is 5 degrees C. So that's going to give us 278 kelvins. And the hot reservoir here is 20 degrees Celsius, and that gives us 293 kelvins. Remember, with kelvins, we don't use degrees because, essentially we treat them kind of like an energy unit, really. Okay, so that gives us the temperatures, and then we can find the Carnot efficiency and know that we are calculating 70% of that for part A. So the Carnot efficiency, we can get that simply by using the equation 1 minus our cold temperature divided by our hot temperature. And we know that the efficiency that we're after is 0.7 of that, right? That'll be 1 minus our 278 kelvins over the 293 kelvins. And that gives us 0.036, which is 3.6% efficiency. So you might, this is something that might be important because say you're looking at doing a feasibility study or something for a power plant such as this one. This is a very low efficiency, but then you could make the argument that yes, but the fuel, quote unquote fuel, right? The temperature differential is something that's naturally occurring. So if that's something that's sustainable, that would be something that you could get at as essentially a free resource. So maybe that you would put up with the low efficiency, for instance. Anytime someone's building any kind of power plant, they have to do a feasibility study and look and see, is it worth the cost of construction and maintenance, et cetera, for the power plant. Okay. Okay, so that's part A. Part B, now we have the efficiency. That's useful. Part B asks us, what is the rate of heat input needed if we want this to be a 500 megawatt power plant? So power plants are often rated by the amount of power that they are able to produce for communities around them. So this one, say if your study was about saying, okay, we could build this power plant, but what's needed by the community is a 500 megawatt power plant. So what kind of heat input would I need here? And they're asking, of course, for the rate of heat input, which makes sense because they're asking us for a rate here when it comes to the power, right, that they're hoping to produce. So power is, of course, just the work done by the heat engine over time. That's the useful thing that you get out of it, right? So let's remind ourselves of that. So power is equal to the work over time. That's given to us in this problem is 500 megawatts. And so we could write that as 5 times 10 to the 8 joules per second. Mega is 10 to the 6, right? And then I'm turning the 500 into a 5. That gives me 2 more places. So efficiency is for a heat engine equal to the way to think about this conceptually is that it's all in the numerator is always what you want to get out of the system, like your reason for building the system, and in the denominator is what you have to put in. So the reason that we build a heat engine is to get work out, mechanical work. So that's what goes in the numerator there. And what we have to put in is the fuel essentially, and that's our QH for heat engine. So QH goes in the denominator. So if I solve this for QH, which is what I'm interested in, right? They want to know what the rate of heat input is, which is essentially the fuel that they're asking for. That's going to be the work divided by the efficiency. So um, if we're interested in QH over time, which is what they're asking us for the rate of heat input, right? That'll be equal to work over time. A way to think about this is work over time, right? Divided by efficiency, which is going to be our power that we're given divided by efficiency. Okay, cool. So power I know is 500 megawatts. I'll put that in SI, 5 times 10 to the 8 joules per second. And our efficiency, as we know, is 3.6%. We need to write that in a decimal form when we're using it in a calculation. And what we get here is something like 1.39 times 10 to the 10 joules per second. Okay. So that gives us the rate of heat input. That is in joules per second, right? Let me kind of box up my answers here. How many joules per second of heat input needs to come into the heat engine in order to produce the 500 megawatts. So, that's still all very theoretical. And then part C here makes it a little more physical and asks us, okay, so if that's the rate of heat input we need, what kind of flow of water does the plant have to take in? And then this is where you would look at the water flow, think about the equipment necessary to handle it. Could the site handle it that you're building this thing in, all that. So we need to figure out now how much water cubic meters per second is the plant going to be having to take in order to produce the 500 megawatts. So cool. We know this is about a change in temperature. So that kind of brings us back to calorimetry, right? Whenever we have water isn't changing phase here, it's just changing temperature. So that means that we're extracting some energy, right, from that temperature change. So I'm going to turn this into a rate. This problem I like a lot because it's about rates in the real world. This is how things work. So Q over T, I'll make that into a rate. And I'm going to relate that to if I take one side of the equation and divide it by time, I need to do the same thing on the other side. But we need to keep this physical so that we know what we're talking about, right? So on the other side, what would make sense to divide by time? Not the C, that's a constant, right? You could say the change in temperature happens over some time, but what they're asking us for in this question, right, is they're asking us for how much water is the plant taking in. They're not asking us how quickly is that water changing temperature. They're asking how much water. So what I'm going to do with this time is I'm going to divide the mass by it, and I'm going to think about that as mass per time multiplied by C delta T. That's a conceptual decision to make there, right? Is keeping your eye on the ball conceptually. As you've probably noticed with these heat engine refrigerator problems, the math isn't all that hard, right? The equations are kind of small and well defined, but the concept is huge for these problems. So we need to keep that in mind. All right, so I'm going to solve this. I know that the mass per time, actually volume for time is what they're asking for, but I know the density of water. So if I find the mass per time, I know I can find the volume per time. That part would be trivial then. So solving this for mass per time is equal to that Q over T times 1 over C delta T. And that, remember, that delta T is change in temperature there. I'm interested in, this is water, right? So the C value is the specific heat there of water. QH over T is what I'm looking at here. So now let's define this. This Q isn't just any Q, it's the Q that is going to be our fuel. Remember, it's the change in temperature, or the temperature differential, I should say, that serves as our fuel for this, right? The QH, the hot reservoir. The cold reservoir is the exhaust. The hot reservoir is our fuel to make the heat engine go. So I can write it this way. Now we have Q over T. We've already defined that in part B. Delta T is the temperature difference in the water. Using the density of the water, we can easily change mass flow rate into volumetric flow rate. We remember that volume is equal to mass over density, right? So if I want the volumetric flow rate, it's essentially the mass flow rate divided by density. So all I need to do really is to place a density term in the denominator of what I'm doing here. So let's do this. This is going to be QH over T, which I've solved for in part B, times 1 over specific heat of water, density of water, change in temperature of the water. Okay, so all we need to do now is sub in our values for these things. The QH over T I solved for in part B. You can look up specific heat of water, density of water. The change in temperature is, we can look at our temperatures here. The change in temperature is 15 kelvins there. And when you do that numeric calculation, you can find the details of that in the written solution. You will get something like 221 cubic meters per second as far as the water flow. And that's something that, again, if you were looking at building this thing, you would have to look at the equipment necessary, look at the site, see if that would work at all for the site of this power plant. Okay, so that's just a basic idea of a power plant. And as I said at the beginning, I like this one because it reminds us that really all we need to create a heat engine is a temperature differential, a hot reservoir and a cold reservoir.